PNCWA members to Bonnie Lake, Washington. It's the home of the Cascadia Wastewater Treatment Plant. I'm John Kircher, and I'm an operations supervisor here at Pierce County. I want to thank you for joining us today, and I want you to know we're excited to bring you along on a tour like you've never seen before.
We're here with Chris Stoll. Chris is the engineer that's the project manager for the design of this plant. Chris, tell us how Kennedy Jenks got involved with Newland to build this facility.
Yeah, well, in 2012, Newland was looking to start up this development again. It had been the Cascadia development. It was transitioning to the Tahali development. And so at that point, they knew that they needed to bring on an engineer to help plan the facility. And so in 2012, I got involved helping with the planning. I was working with our team, essentially laying out what the facility was going to look like, how it was going to support the different phases of the development. And then, we moved into design, moved into construction, and we got to build this plant, and it went online in 2018.
So Chris, what's unique about the Cascadia Wastewater Treatment Plant?
Yeah, there's a couple things that are pretty unique here. First is that it's a greenfield plant. There aren't many treatment plants that we get to see that are built from, this was essentially a gravel pit, and now it's a treatment plant. So, trying to talk about, bringing in all the utilities, so first time power, water, sewer, all those different pieces had to be considered here. At a lot of facilities, those are already there. And so you're able to, build off of those, and you're able to expand an existing plant. And so this one was pretty unique in that it was greenfield. The other unique part is that it's developed for phases as well, because the Tahali development is a 5,000 acre development. A significant number of homes are going in. We wanted to make sure that the treatment plant could be expanded to meet that pace of development, but not be something that was in construction all the time as well. So that was pretty unique. The other really unique part about the project delivery of this was the partnership between Pierce County and Newland. So with Newland being the developer for the development here, and Pierce County being in a place where they can own and operate the facility, that partnership that had to be used during the planning, design, and construction was really unique with this process.
What are some of the benefits that this private and public partnership has afforded the county?
Yeah, that's a good point, because that partnership was pretty unique between Newland and Pierce County, and what it was really meant to do is help increase efficiencies, which is what we see with these kinds of partnerships in other places too. So, the great part about the county is that they had the infrastructure, they had the knowledge, they had the staff to operate these kinds of facilities. Just things like asset management programs, making sure equipment's maintained on time. So that's what the county is really good at, and what they do day in, day out. They maintain their Chambers Creek facility, a collection system, pump stations. So, they've got the people on staff to really make that happen. Newland, on the other hand, being a private entity leading this development, they're able to move really quickly. They're able to get the right contractors, consultants, support that they need to make those projects happen. So that's a good way that partnership can leverage the benefits of both the public side and the private side.
What are some of the challenges that Kennedy Jenks and you faced as a PM in designing this facility?
Yeah, there's a couple things that were challenging in design. First was, looking at the facility as it would be now, operating it at lower flows, but then understanding what the future flows would look like. So making sure we were sizing equipment, sizing the transformer that comes into the facility, making sure those things were things that didn't need to get pulled out, right away, or, during the next phase, making sure that those were there to support the facility as it went along. So trying to make those next stages easier. So trying to really focus on that. And because it was a new development, trying to assess where the flows were going to come in terms of, flow per household was challenging. There's some rough numbers that we use, there's some typical numbers, but with this being a new development, new collection system, the use of low flow, fixtures in homes, that sort of thing, really trying to kind of figure out what was going to come into the plant initially was challenging. And then a pretty unique part too is that usually treatment plants are built at the low point of a collection system, and then they flow to an outfall, like to a river, to the Puget Sound. And at this plant, that's not the case. So the effluent actually needs to get pumped back up the hill to a drain field for discharge. And so the way we design this is we actually have the membranes pipe right to the pumps that then pump up to that. So making sure that control strategy of how the membranes operated and those pumps was really a challenging piece that we worked with during design, and then we had to work a lot more with the integrator as we were commissioning the facility, bringing it online to make sure that could work.
And it's an existing drain field too, is that correct?
Correct.
Yeah.
It's an existing drain field. One of the things that's unique out here is actually the subsurface geology. There are some pretty permeable gravel layers that are out here, so you can get a lot of that effluent going into the ground in places. There are some spots where there's some impermeable glacial till out here that we had to fight with a little bit at the treatment plant, but there's a lot of spots where that effluent actually gets just discharged to ground. And so there's an existing drain field right now, but there's plans to build future rapid infiltration basins as well as the flows keep going up.
Tell us a little more about this phased approach that keeps pace with that growth.
Yeah, absolutely. So we designed the treatment plant to be expanded in 4 different phases. So what that looked like is we wanted to make sure that the first phase was able to treat about 3,500 homes worth of flow, and then we built it so that those additional treatment trains could be brought on essentially right next to the existing treatment trains that are there. But what we did too is we wanted to make sure that buildings were sized so that you didn't have to tear down walls or tear off the roof, expand buildings. So the mechanical building that's right behind us is a good example of that. There's a lot of places there where you can add in new blowers, additional UV treatment units, additional pumps, those sorts of things, such that the plant can be expanded by just adding equipment within the existing spaces. One thing we did too with the chemical room is we actually put a false floor in. So right now there's totes, some temporary storage tanks, with the idea that there would be larger tanks put in the future. But we didn't know what those sizes were, what would be needed there, just because we weren't sure how the plant was going to operate exactly. So we actually put in a false floor that can be pulled out, and then permanent tanks can be put in later. So we tried to add stuff in like that really helped us provide some flexibility for the future, so that any sort of expansion would have as little impact on the operators and the operation and the maintenance of the facility as possible. The piece that's really hard to consider that sometimes we forget about is what are those low flow conditions though too. We're always talking about what's the max flow, what's the highest loading, but when we start up these plants, especially here where we are seeing lower flow per household than we thought, it's what do those low ends look like and what are the challenges there. And I know we've worked a lot with Pierce County on the flux rates on the membranes and the low operating points on the pumps too. So we want to make sure those pieces of equipment are still operating well, but we have to make sure to check the range of those different pieces of equipment.
Right, so it's a big benefit then to know what build out looks like in the very near term as you put in these facilities, as you leave those empty spaces for equipment.
Correct.
Awesome.
You want to be able to expand it as it needs it, but not too fast, because then the operators are stuck with this facility that's oversized,
Right.
and they're having trouble making it work.
What are some of the challenges that we're going to face as this development continues?
Yeah, I think one of the obvious pieces is just keeping up with what the flows are going to be coming into the plant. There's typically requirements in a permit to, when you get to certain percentages of capacity, making sure what's coming next, how you're going to maintain your treatment performance, maintain your capacity in the plant. So we've been working really closely with the county and Newland to keep an eye on that. Newland has a specific schedule for how this is going to develop, and so we've been correlating that to what's coming into the plant, make sure we've got an eye on when those construction phases need to take place. Another piece is that right now the treatment plant sits within a lot of undeveloped land, and so as the community keeps developing, there's going to be some new neighbors that are going to be around here. I don't remember exactly what Newland has planned, but making sure that those people understand what this facility is and that it doesn't smell, it operates well, those sorts of things. So as the flows keep expanding, and as we talked about earlier, that it goes to a drain field, right now there's going to be a final rapid infiltration basin that's going to get put in. So right now Newland is looking at some locations for that, and because that gets discharged to the ground and to groundwater within the area, we need to make sure that one, the ground can handle those flows, and that two, any sort of water quality impacts from those are mitigated as well. So the plant right now is designed to reduce nitrogen in the flows so that it can meet groundwater standards, and so that capacity and that treatment is going to be kept up through the life of the plant so that it doesn't affect groundwater in the area.
Gotcha.
Things like nitrates, those sorts of things can have an effect on public health and the environment, so we want to make sure those things are taken care of. The other piece that we're always looking at too with the plant, especially with a membrane bioreactor plant, is that the equipment keeps evolving. There's a number of different membrane systems out there. Some work better in certain circumstances than others, and so making sure we're keeping an eye on where those membrane technologies are going. In the past, when we've put in membrane systems, we've assumed like a 10-year life, essentially, right? Knowing that the systems are going to improve, that are going to increase, but sometimes those facilities don't always reach their capacity. But this is pretty unique in that there will be expansion of the plant because we're at this development that keeps growing. And so, those times when we have to look at new types of equipment and the evolution of those treatment technologies is going to be on our doorstep, sooner than a lot of other facilities just because of the growth here.
What are some of the goals and opportunities that Kennedy Jenks has in the completion of this project?
Yeah, there's a couple things there. One with the Tahale development being essentially a closed system, meaning that it has its own treatment plant, it has its own collection system. There's some opportunities here for reclaimed water, reuse of biosolids on site. Kind of my personal dream would be if we can, reuse all of that within the development itself, right? There's a lot of landscaping that Newland's been putting in, maintaining a lot of the green vegetation up here. So, they've been putting in reclaimed water pipes along, the main arterials through the development and putting in purple pipe for reclaimed water. And with this being an MBR facility, having, nutrient reduction, having UV disinfection, it's just a great opportunity to be able to use that water right here to maintain that instead of needing to rely on potable water. Yeah. And then, biosolids we're a little further out on, but, as we look at some options here for that, you can easily use that for fertilizer up here, compost, trying to maintain, again, that vegetation, trying to keep all that within the system, which would be great.
Yeah.
And in addition to, we've been working with the county for a long time. The county's looking at ways to, within their collection system, to provide places of other treatment, looking at places they could provide reclaimed water. And so this is a good opportunity for the county to see what it's like to run a pilot, essentially for these satellite type facilities, to see if that's something that could help the county in the future as they're looking at their collection system and planning things.
Yeah, that's awesome. Chris, any last thoughts?
I would just say, the development is growing. Pierce County's out here taking control of the plant, and just, that partnership, that development, looking to the future is, what the team is doing right now of making sure that this treatment plant can keep performing and keep serving the community, keep protecting the environment.
Oh, I 100% agree, Chris. I can't thank you enough for your time.
Yeah, thanks, John.
want to introduce you to Dennis Cossett. Dennis is the lead operator here at the Cascadia Wastewater Treatment Plant, and he's going to be taking us on our tour. So Dennis, tell us a little bit about your history coming here and helping start up the plant.
Yeah, so I've been out here at Cascadia for about a year and a half. Previously, the county had been operating as a satellite facility with rotating operators, and I came out here as a full-time operator 5 days a week with maintenance support. Currently, the plant receives about 300,000 gallons a day of a 1 MGD startup design. Already working on plans for the next expansion, which will double the capacity and bring in more treatment processes.
Very cool. What are some of the things that you've had to deal with in working to achieve the baseline for the operation of the plant?
Troubleshooting the programming and the automation of a lot of the process, and really just fine-tuning to a large degree, and a lot of that had to do with working with instrumentation.
Yeah.
And then just getting a feel for a good sense of process control of the different variables, seasonal and biological.
Right, so starting up, you're trying to figure out kind of what's normal and what's normal here, and then how to react to that with equipment that we're not entirely familiar with, and we're not sure when it's wrong or when it's right. So that's actually challenging all by itself. It's very cool. So Dennis, we're going on our tour. What are we going to see today?
We're going to start out, we'll go through the headworks, the liquid stream, through the mechanical process, and probably end up at our distribution drain field.
Okay, let's go.
So this is our headworks. We have Huber fine screens. They're the drum style with a pore size of about 3 millimeters. We have 2 existing screens with room for a third.
Dennis, what's the capacity of each screen?
Each one of these screens is rated for 1 MGD.
Okay. And you're currently doing about 300,000?
Yeah, right around in that range.
Okay, so really you don't need 2 yet, well, redundancy-wise, but that's why there's a slot for the third one to come in. When you do pass that 1 or 2 MGD mark, you've still got that redundancy.
Correct, and growing with the flow has been an issue with us because it started out in the beginning phases where we had really low flows. It would cause ragging issues and plugging in the screens.
I see.
But as that flow comes up, we get more velocity and they work better.
I see. They just don't have the throughput through the auger and the compactor to make them stay running and trip outs and things like that. Gotcha.
Correct.
Now, does it produce a pretty clean screening? Like,
yeah, produces exceptionally fine screening. Because of the small pore size, nothing gets through them.
I see. Okay. So we'll check that out later because it is it's remarkable how clean that stuff is when it comes out the other end. Okay, so that's our headworks. What's next?
Out of the headworks into the primary influent channel.
Okay. We're outside the building now. We're just looking at the 2 treatment trains in the influent channel.
Yeah, we come under the wall of the headworks building into our influent channel. We have a partial flume for flow measurement, and then also a sample point for our primary sampler.
Awesome. So through the flume, and then get your flow measurement, and then straight on into the process.
So the influent flow will come up from beneath into our mixing box, and it also meets the return flow from our membranes at the other end of the process.
So you have the return is channelized back to this point. That meets your mix liquor recycle and your influent flow all at one place before it goes into your first anoxide.
Correct, and then we have slide gates on either side for train 1 or train 2.
Okay, so then you direct the flow which way you want it to go. Dennis, would you take us basin by basin through the process and just talk about what we're doing in each phase of treatment?
Okay, sure. So when we come out of the mixing box, we go to the first basin, which is anoxic. And then in the anoxic basin, we have internal recycle and then mixed with the incoming flow.
Mixed liquor recycle, your RAS, and your influent flow are all meeting in that first anoxic, and that's where we're denitrifying?
Starting the denitrifying, yeah.
Okay.
But then from the first anoxic, by gravity, we go to aeration basin 1.
Okay, and then aeration basin 1 is the first aerobic step, and that's where we're getting our carbon removal and our ammonia.
Correct.
Okay.
So we have a DO sensor in the first aeration basin, and then we have a baffle wall, and then we have a DO sensor in the second aeration basin, which are separated on different manifolds so we can have a DO profile from front to back.
I see. So imagine higher DO in the front and then sort of tapering off towards the back once you're done getting rid of that carbon, that ammonia.
Correct. After the second aeration basin, we'll go to a secondary anoxic zone, and if we found that if we carried too much DO into the second aeration basin, it would bleed through.
Okay, I'm with you, yeah. So then after second aeration basin,
then we come to the second anoxic basin.
The anoxic 2.
And this is where we continue the denitrification, and then this is also the location of our internal recycle pump.
Okay.
So from the secondary anoxic, internal recycle returns to the first anoxic.
Okay, so you've got gravity flow through anoxic, aerobic, and then another anoxic, and that's where your recycle heads back.
So then flow from here, we have a feed forward pump that feeds the membrane at the end of the train.
Okay, so pump forward and pump backwards out of second anoxic.
Correct.
Okay.
And so we're set up for a total of 4 membrane basins, but at this stage in the plant, we only are operating on 2.
Okay.
So we have 2 future membrane basins, one of which we've adapted to a WAS storage tank.
Okay, so you store the WAS because there's no solids handling on site, and then it's trucked off?
And it's trucked off.
Okay, so the hauling of the WAS, how's that worked out?
In the beginning, it was a lot easier, but as the plant comes up in flow, so does the WAS demand. And so now it's a pretty constant duty to haul this off.
Yeah, hauling every day, right?
Correct.
Okay, but it's nice to have that tank that you can utilize to store that WAS for the time, because you don't need the membrane. And the other train is all just offline right now, so that's actually extra also.
Right, it's partly redundancy and partly we don't have the flow demand for it, so we run one train at a time.
Okay.
And then maintenance-wise, we alternate.
Perfect. Awesome. It's very cool. Okay, so the last step then is
membrane.
The membranes themselves.
And so we're running one membrane tank on each train, which required a little bit of valving work to be done. Down the road, when this is all set up, it will be fully one train at a time, but we're splitting the membranes across 2 trains.
I see.
And we run them, but we run both membranes regardless of which train we're running up above.
Okay, so you have flow being pumped to here. What's the normal permeate cycle look like for you on these membranes?
Right now we feed forward 4Q of the influent flow.
Okay.
And we're permeating about 80% of the time during the day. It's off of level from the second anoxic basin.
Okay.
So we operate within about a 1 foot of elevation of that anoxic basin.
I got you. Okay, so let me wrap my head around this. The liquid level in the anoxic 2 actually fluctuates throughout the day because this section needs to go gravity back to there and that section needs to go gravity to there. So really anox 2 becomes an important piece of this whole thing with how much you can permeate and how much you can... I got you. Okay, so that's very neat. It seems more complex than it is, I know.
I know.
80% of the time probably permeating on one or on both?
They're linked together at the present time, so they permeate at the same time and they relax at the same time.
Okay.
That was for simplicity of valving.
What kind of TMPs do you see?
So on average, right now we have a TMP of about 1.5.
Okay.
And that will increase obviously over time as we get closer to need for a CIP or a cleaning.
Right, and just as you push that GFD up too, right? Like, because what's your flow rate right now in comparison to the capacity of the membranes?
Oh, we're at the lower edge of the flow rate.
Okay, but still, that's good. I mean, 1 on TMP is great. Do you know what your GFDs are?
I think our GFDs are right around 6.
Okay, so not too bad. Okay, so then flows here, you're permeating 80% of the time. Then your return comes off of this tank also by gravity?
So I said the feed forward pump is set at 4Q of influent flow. So if we're permeating 250 GPM out of this basin, the feed forward is 1,000 GPM.
Okay.
And then that excess flow goes over the weir and is the return.
And that keeps solids from accumulating in the MBR.
Correct.
Yeah, okay.
And that's one of the things we've had to play around with is what speed to set the feed forward at so that the solids stay distributed evenly.
Yeah, because we did get some stacking in the MBRs initially, right? Where it's quite a bit higher in solids concentration than the rest of the plant.
Yeah.
Yeah, okay. How about waste? Do we waste out of here?
We waste out of the return channel.
Okay.
We have just a valve that is below grade, so when it's on a timer it will open, and then we get the volume off of the level of the waste tank.
Okay, so you just have to open a valve and then drain to that lower level on the waste tank, and that's your calculated wasting for the day.
Yeah.
That's awesome. That's pretty simple. What's a neat process, Dennis? Where are we going to next?
Next we'll go down to the mechanical building.
Okay. So one more thing, folks, we had an opportunity to do a CIP, or clean in place, on the membranes here, and we wanted to check back in and just give you a little bit more information about that CIP and let you see a little bit more of the membranes themselves. Dennis, can you tell us about the CIP, and then we'll take a closer look at these membranes.
Yeah, so on a scheduled basis we do a clean in place, which is where we take the membrane basin offline, back flush it with a chemical, typically sodium hypochlorite or citric acid, to clean the membranes from the inside out to flush out any lodged debris or solids. We let that sit for a soak period, and then we back flush it again with processed water.
Okay, so you're actually pushing chlorinated water backwards through the membranes to push material out and disinfect and clean those pores.
Correct.
Gotcha.
And then when we take that opportunity, usually when we have them offline, we drain it out, clean it out, and check for damage and debris and any maintenance needs that are there.
That's very cool. Awesome. Let's jump in there and take a look.
Okay.
Okay, Dennis, so describe to us how the membranes are doing what it is they're doing.
All right, so you have here on the top, we have the metal air influent pipe. That header brings all the air down to the bottom of the cassette for air scouring up through the membranes to keep the solids from dewatering and lodging in there. And then out the side we have our permeate line, which is what sucks out from inside the membrane, and you can see how the permeate line runs through each of the membranes at the top and connects them all together.
Each one of those sheets picks up that same pipe.
And then the permeate pipe takes it out and away to the UV disinfection.
Okay, so that's happening continuously while this basin's being fed from feed forward. So you have the influent flow of that high concentration mixed liquor, and then clean water escaping through permeate. And then how about air scouring on the bottom, you said?
Yeah, the air scour is up from the bottom and it goes into a scour and relax. So it will always scour while it's permeating, and then when it's not permeating, it scours and relaxes to help dislodge those solids.
Okay, so that's there literally to break up the material that's getting stuck on those sheets as it pulls that suction on them. Well, that's very cool. It's very interesting. It's a lot more simple once you see the water out of the tank.
Right. So now we're beneath the treatment trains and beneath the membrane basins, and then you see down this hallway, here's all of the piping for each leg of the membranes. So Well, on this end we have, this is train 1's membrane, and then as we go down on the other side would be train 2.
Okay, and we got piping for, it says LPA and perm.
Yeah, so we have the air scour lines that run up beneath each membrane cassette, and then we have the permeate lines that are pulling from inside the membrane.
Right, I gotcha. And then those are just staggered and everything in the galley below?
Most of the below is just, we have rotork valves to balance, because we run both sides at the same time, we have to have the rotorks to balance the permeate coming out and the air going in.
Very cool, very cool. And all the blind flanges you see on the wall, those are for when the new membranes are added in those other basins.
Yeah, all
That's
the
very
piping
cool.
and valving is already in place, so we just have to make the connection and put the membranes in.
Awesome, that's very cool. The water quality from membrane facility, that's a 0.04 NTUs, that's pretty amazing. So what about the wasting, Dennis? Where's that all moving when we're down here?
So above us is the future tank that we're using for WAS storage. It has a drain that comes gravity down to us to a rotork and a flow meter,
Okay.
and then it goes through the back wall for our truck loadout.
So that'll get the flow into the trucks, and then you guys also have a decant on that tank, right? An interim decant function?
True, we have a telescoping valve that we can operate up top that will drain off the top of the tank, and that goes through a separate drain line into our implant pump station.
And what was the experiences with trying to use that decant?
Well, it seems to be process and weather dependent. When at certain times the sludge settles rapidly and you can decant off the top,
Right.
but at other times the sludge floats rapidly.
Right.
So we kind of had to play it by ear and either decant off the top or decant off the bottom.
Right, okay. Also, you have to aerate that tank too, right? So there's some considerations with when you can aerate it to keep it fresh and not smell bad, and then also still be able to settle it out to decant it.
Yeah, that has been another one of the challenges, where trying to stretch out that window as far as possible without causing an odor problem.
Right.
And also weather dependent on, faster settling
Sure.
in summer times.
Plus
slower.
coordinating the truck to be here. Yeah, that's awful. Yeah, that's tough. Well, I'm glad it's working out. All right, so what's next?
So we saw the permeate lines coming down from inside the membranes, and then that's driven by our permeate pumps.
Okay.
And we have 3 pumps installed with room for a 4th. 2 of them are roughly 500 GPM piece, and then we have a larger pump that isn't in use, partly because where we discharge into a drain field is temporary,
Right.
and we're going to go to a rapid infiltration discharge later, which we can, as our discharge goes up,
Right. So you can potentially pump quite a bit more, take advantage of that low GFD that you have now and push that stuff out and reduce that permeate time. That's awesome. So 2 small pumps that you use now, 1 large pump that you don't use, and then space for a further. Right on, that's very cool. So these are the pumps then that push up the hill to the on-site septic up there.
Right, they're doing kind of double duty. They're pulling through the membranes up
Okay.
top, and then they're also pushing it up the hill.
Gotcha, yeah, it's very cool.
And they pull out of the membranes, and then they push through we have 2 Wetico sealed UV reactors.
UV pumps actually run through the Weticos, and then that same pipe goes up the hill to the LOSS. That's very cool. So you still have lots of room for new equipment to be installed, lots of pipes sticking out of the ground in places. How about the non-potable or the reuse water on site?
So our reuse water is pulled from our discharge line about halfway up the hill to our drain field. It's pulled out, pumped back through with our pumps.
So you can take advantage of some of the head provided by that long discharge in maintaining pressure down here at the pump. That's very cool. Okay, so that's most of mechanical. What else?
Next to this room, we have our blower room, which is both of the supply air for the membranes, for the air scour, and our process air for our aeration.
Gotcha, so all the blowers are going in that one room.
Right. So down one side of the room, we have our MBR blowers, which are all the air scour for the membrane cassettes. And we have 3 installed and room for 2 future.
Okay.
And they're our larger blowers.
Right.
And then we have, down the other side is our process air blowers. And the same, we have 3 installed and room for 2 future.
Right, okay. How many blowers are running typically today?
Typically today, 2 MBR blowers are always in service for the air scour, because that's a fixed airflow for the number of membranes we have in service.
Right.
And then for the process air blowers, that is dependent upon the demand.
Loading in the reactor, okay. Yeah. So where are we headed to next?
So next we'll go to our chemical feed room, and then we'll finish up with our screening room.
Awesome.
So in our chemical feed room, it's split into 2 injection sites. We have magnesium hydroxide for pH buffering, and then we have micro C for carbonate source.
Okay, so micro C dosed for denatrification. Do you use much micro C?
To date, we haven't used any micro C.
Okay, haven't needed it at these low loading rates or low
Right.
flows. How about magnesium hydroxide?
Magnesium hydroxide is variable, mainly dependent on the season.
So when you run that magnesium hydroxide, is that like a constant thing, or is it just turn the pump on every once in a while? Like how complex is the delivery of that alkalinity?
It's more of a process dependent addition, and we don't run it full time. We augment as needed depending on the effluent pH.
So you can kind of watch that pH fall a little for a few days and then decide to put some online, run it for a few days or maybe even a day, and then boost that pH right back up. So it's not that difficult to maintain.
No.
Yeah, I gotcha. Okay. All right, so we're done with chemical handling. Where are we headed next?
Next we'll go to a screening room.
Okay. Okay, Dennis, so we're in the screening room.
Our screening room is located directly below our headworks, where we have a long conveyor that drops it down a chute through the ceiling and into our dumpster.
Just a discharge through the dumpster, and it looks like...
It looks like shredded paper. You can see how fine those...
Reminds me of the Build-A-Bear.
Right.
So next is the drain field?
Next would be our drain field.
Okay. So Dennis, we're at the drain field. This place is huge. Can you tell us what's happening once the flow comes up the hill here?
From the plant, the permeate pumps pump it up to an existing septic well, and then that pump station pumps it up into our drain field.
Okay, so there is another piece, there's another component there in the line, the permeate lines. They don't come directly to the drain field then?
No, and in the future, the septic well that we're using as a pump station will be eliminated and we'll go straight to a rapid infiltration.
Okay, so that's probably part of the whole capacity. As it increases, you need that flow more. Well, this is neat. It's very, very big. Well, Dennis, I just want to say thanks again for taking us on the tour, and we're really excited about what the future holds for this plant.